In this video we're going to take a look at what we mean by chemical equilibria. Now, equilibria is something that you've come across at GCSE, and you will have come across these arrows that we have here. If we just have a look at these arrows here represent a reaction that is reversible and therefore in equilibrium. So we have these double-headed arrows, and you should have come across those at GCSE, but let's just take a minute to think, what does that mean to us? A and B are in equilibrium with C and D. So at the start of the experiment you have to start with something, so you start with your reactants A and B and you put them in a beaker, and the reactants start to collide, and as they collide they convert into products. So you start to see the point where on the other side you have created some C and some D. And as soon as you've got enough C and D there to collide, C and D will start to collide with each other and they'll convert back into A and B. So actually, you don't have either of these two beakers present. A system in equilibrium, when it reaches equilibrium, will have some of your reactants, A and B, but also some of your products, C and D, and they're all present in your beaker. So once we establish equilibrium, we've neither got our reactants, here or our products here. When we're in equilibrium, we're in a system where we've got both the reactants and the products present, and they're converting backwards and forwards to each other at the same rate. So you could imagine a couple of scenarios that would be similar to this. You're digging a hole, but your best friend is filling that hole back up at exactly the same speed. And so what is in your box at equilibrium is what is in your hole. Your hole is exactly the same size. Your box is full of exactly the same things. So once you're at equilibrium, you've got reactants and products present, not just one or the other, reactants and products present, and they are staying at the same amounts. They are staying at a constant amount. They're not the same as each other, they're at a constant amount. So the next statement says it can only be established in a closed system, and it could be set up from either direction. So let's take a look at what that means. So it can only be established in a closed system. That means that if D had been a gas, it would have started escaping from, so if D was a gas, it would have started escaping from our beaker, and then it couldn't collide with C to go back. So if we want equilibrium to be established, we need to close our system off so that nothing can escape. We can establish it from either side because we know that D and C convert to A and B. We know that A and B convert to C and D. So we can reach this equilibrium position from either direction. Okay, so at equilibrium we're in a natural balance between the products and the reactants, and it's dynamic because both things are still happening. Imagine you go to the shopping centre and you go on the down escalator, but you walk up it. As long as you walk at the same rate as the escalator, you won't appear to move, but you are moving. So it's dynamic, it is happening, but it is maintaining some sort of stillness. So we call it dynamic because it's moving, but equilibrium because it's maintaining some sort of position where things don't change. Right, so what are the key features? If you're asked the key features of dynamic equilibrium, the first thing you're going to write down is rate of forwards equals rate of reverse reaction. How could we show that on a graph? So what we're going to plot is we're going to plot a graph of rate. So we can see that the rate of the forward reaction and the rate of the reverse reaction over time. I'm going to use two colours. I'm going to take my forward reaction in one colour. At the start of the reaction, the forward reaction will be going much faster than the backward reaction because there are no products yet, so the backward reaction can't be happening yet. So the rate of our forward reaction is going to start quite high up. And during a reaction, at first, when there's lots of reactants, it's going to be going quite quickly, but it's going to slow down. So it's going to come down and it's going to slow down until it levels off, until the rate maintains a steady value. And our reverse reaction, this is our forward rate. Put forward reaction, because we've measured rate on the side. How does our reverse reaction differ? See if you can have a think about how your reverse reaction would differ. So if you've managed that, you should have started at 0, because at the start of the time of the reaction there are no products, so the reverse reaction isn't happening, but gradually as products form from the forward reaction, the reverse reaction starts to speed up. So as you get more C and D, that conversion back into A and B starts to speed up and speed up and speed up until you hit the point where you're digging the hole as fast as somebody is filling it, where nothing appears to change. So at what point on this graph could you say equilibrium has been reached? Look at the statement we've highlighted in green. At what point has equilibrium been reached? So as soon as those two lines hit the exact same value for rate, remember that rate is on our y-axis, so as soon as they hit the same value for rate, then we have reached equilibrium. So equilibrium isn't achieved immediately, it's achieved after a period of time. So you put your reactants in the beaker and you leave them for a period of time, and then equilibrium is achieved. Once equilibrium is achieved, it's like walking up that escalator backwards at the same speed. You're not going anywhere, nothing is changing now. So that's feature number 1. And remember, if we're asked what we mean by dynamic equilibrium, the second thing we say is the concentrations of the reactants and the products will remain constant. Be careful with your words. They're not the same now, they're constant unless conditions are changed. So what do we mean by equilibrium lies to the right, and what do we mean by equilibrium lies to the left? Equilibrium lies to the right means that once we reach equilibrium we've got more products than reactants, and equilibrium lies to the left means once we reach equilibrium we've got more reactants than we have products. So remember, we're not in the middle. That's a common misconception. Equilibrium doesn't mean you are in the middle, it just means that you are staying at the point that you have reached. So when we say the equilibrium lies to the right, we mean that at that point we've got more products than reactants. So how could we show that on a graph? And on our graph we're going to plot concentration against time on each of these graphs. So pause the video and have a little think about what you might want to draw. So if equilibrium lies to the right, then as we start our reaction, we start off with lots of reactants, so nice and high, and if we're going to lie to the right, we're going to turn them into lots of products. So they're going to drop, and they're going to drop quite low. Not going to drop to 0 because there's always going to be some of them there, because remember they're always being reformed, and they are our reactants. They started off high and they ended up low because our equilibrium lies to the right. What we mean by that is more products than reactants at equilibrium. So how would our products curve look in blue? So at the beginning we start with no products. How would it look? So pause the video and see if you can draw it. So our line should be curving upwards this time, and what we need to be clear is, unlike the graph above, these two lines don't then proceed at exactly the same value, because we're not saying that their concentrations are going to be the same, we're saying they're going to remain constant. So looking at the sentence highlighted in green, can you mark on the time at which equilibrium was achieved? Now, a common misconception is to highlight the point at which the two lines cross. That is not what the highlighted bit in green says. It says when they remain constant. So we want to find the point where the products and the reactants lines stay level, remain constant. Their concentrations are constant. So this point is where equilibrium is achieved. So their concentrations are remaining constant. We've got more products than we have reactants, so we know it's an equilibrium to the right, more of the stuff on the right than the stuff on the left. Could you have a go now, pause the video and see if you can plot the graph for equilibrium to the left? So if you've managed that you should have something like this, where the reactants are coming down, the products are going up, but in this, when equilibrium lies to the left, we've got more reactants than products. It's not a very good conversion, and therefore at equilibrium the reactants line is staying higher than the products, but equilibrium is achieved when the two lines go level, so flat. Not the same as each other, but they're staying the same as themselves from that point onwards, so they are constant from that point onwards. So make sure you understand what we mean by equilibrium and what we mean particularly by the terms dynamic equilibrium. So rate of forwards equals rate of reverse, and concentrations of the reactants and the products remain constant.